Okay, so I don't have time to go over the motivation for this, but trust me, there's a reason for this method of proof. Maybe next time. Or yeah. So let X be a set. And then we also want a collection. A collection of subsets of X having the finite intersection property. Finite intersection property. I'm going to call this in short FIP. All this means is if you take a finite intersection, you're not going to end up with an empty set. There's always going to be at least one element in that intersection. Then there's going to exist some collection, we can call it script D, of subsets of X such that the collection A is contained in the collection D, and D has the finite intersection property, and no collection of subsets of X, that properly contains the collection D has this property. And for the rest of the proof, we often call such a collection D maximal with respect to finite intersection. Respect to finite intersection. Okay, so here's the gist of the proof. We want to be able to take an arbitrary product of compact spaces and get a compact space. We're going to do it through the closed form construction of compactness. Very rough motivation is going to be if we took the example where we're looking at 0, 1, so this is 0, here's 1, and if I take, say, 1/2 and maybe a third or something, and then maybe 2/3, then if I have these be the coordinates of foci for some ellipses, so this is going to have this some sort of ellipse in here, and then we're going to collect all of the closed subsets inside of here, etc., etc. And then the idea is we want to always be able to choose an X in here that satisfies the finite intersection property. The issue is if I choose, because when we drop these down and project it onto, so it's like x1 to be x2. So if we choose an x1 here, then if we choose our x2 somewhere here, then the point that we're going to get x1 cross x2 is not necessarily always going to be in that intersection. So this would be what we call a bad choice. So we'll fix having a bad choice by imposing essentially an expansion on what kind of closed sets we're taking. So that x1 is 0. Now, in this particular specific example, if I restrict it so that I expand my collection, where now these points are relevant only for the sake, so if I call this line segment, and so the set of all of the foci, if I push this down, then I can have, we'll start here, that as it decreases, it's coming down closer and closer and closer to there. So that way that's gonna force me to choose my x1 to be here and my x2 to be this one. And so that point x1 cross x2 then is always going to be inside of the finite intersection. So the idea is, okay, this is great for this example, but then speaking of this in arbitrary terms, we're generalizing, we're finding that expansion of sets. So that's what this D is, this idea, is we're trying to find a maximal uh, collection of subsets so that it essentially here it just forces us by property the finite intersection property to make the correct choice. In other words, to guarantee the existence of at least one element in the intersection so that you never have empty intersection. And then because you always have a correct element you can choose for every intersection, you're never going to have an empty finite intersection, which is going to give then closed form compactness. So this can then be generalized in the very last step to just will index this to a number of compact spaces and then projecting the take the projections in an arbitrary number of times. So this is a rough outline. This lemma, the first step of just saying we can claim that there does exist this maximal collection, from which that'll essentially force the intersection to be something that will be inside of the finite intersection.
It doesn't have to be unique, right?
No. It's just in this example, it happens to be unique, but it doesn't have to be. Because when we expand it to the general product, it'll be like a neighborhood around the point, and then the inverse image of that neighborhood will be contained inside of that subset in the collection. Okay. Anywho, let's prove this. So we construct script D using Zorn's lemma from last semester, and I'll reproduce the motivation here. It states that given a set A that is strictly partially ordered, so that's a type of relation in which every simply ordered subset has an upper bound, A itself has a maximal element. So the set A, to which we shall apply, Zorn's lemma, is a set whose elements are themselves collections of subsets of X. So for purposes of this proof, we will call these supersets. So I'm going to give a summary of notation. We're going to call, so C in X, that's C an element of X, capital C a subset of X. And then what we've been doing is we take collections, script C, it's a collection of subsets C. And then now what we're saying is we got a superset. So we'll take and we'll denote it like this. So this is not complex, we just need something. So this is the superset, which is a collection of the collection C, which are then collections of subset C of X containing element C in X.
Why do we have more than one collection?
Because we're comparing all the different kinds of collections so that we can find the maximal collection, essentially. So in order to find the maximal thing when we're talking about collections, now we need to put that idea into the set itself, which could be compared with all the other kinds of things. If there's going to be a notion of which one's maximal or which one's not. Um, okay. So by hypothesis, we have a collection. Have a collection script A of subsets of X that has the finite intersection property. So that has the finite section. So then what we're going to do is we'll say this double scripted A superset. This will denote the superset consisting of all collections script B of subsets of X, such that we'll have that script A needs to be contained by, it's gotta be, we'll contain the collection A in B, where B has the finite intersection property. So we use proper inclusion. Use proper inclusion. All that means is like strictly as our strict partial order on the superset double struct A. And to prove our lemma, we need to show that this double struct A has a maximal element. So we've reframed essentially the goal of the lemma into the language with the supersets. Okay. So that we can apply Zorn's lemma to it specifically. So in order to apply Zorn's lemma, we must show that if I take double struct B, so if B is this is fun, sub superset. So it's a superset, but now it's a sub superset of the superset.
Sure.
Of A, double struct A, that it is also simply ordered by the proper subset relation. Then this subsuperset has an upper bound in superset A. So here's Zorn's lemma saying, here's you take strictly partial ordered, so then every simply ordered subset then has an upper bound. So we're applying that now to the situation. This A has become the double struct A. The subsets is now the sub superset, and now we're claiming that the sub superset has an upper bound. So if we can end up showing that, then the actual conclusion then of Zorn's lemma, which is that the original set, so that A has a maximal element, and we'll just call that maximal element that we find the script D. So we shall, I erase my proof. Okay. We shall show, in fact, that the collection And I can define now a new collection as taking the union of the collections B inside of this sub-superset B, which is the union of the collections belonging to B. Or I should say, I gotta be careful which B I'm talking about since the sub-superset is an element of double struct A. Because then it is the required or bound on our sub-superset. So to show that this collection is indeed even in the original superset A, we must show that our collection A is contained in this collection C, and that C satisfies the finite intersection. So certainly, the first part's easy. Script A has to be contained in script C just by nature of how we define script C, since each element of our sub-superset from which we're defining C contains A. So that's going to come definitionally or by choice. So to show that then our collection has the finite intersection property, we're going to let C1, and we'll just take a finite number up to n of subsets that are elements of this collection. So that's why I'm not putting the subset thing there. Then because C is the union of the elements of sub-superset B, then that means there's always going to exist one such collection, we can call that script bi, for all I, such that that subset Ci can be actually found as an element of one of those collections, indeed. And the superset, where now I'm just going to do this for all of them, so B1 to Bn corresponding to the C1 to Cn, is a subset of the sub-superset B. So it is simply ordered. That's induced from the sub-superset by proper subsets. And so being finite, just up to n, it has a largest element. Largest element. So that is, there exists an index k such that I can take the collection B sub I, that's always going to be a subset of the collection B sub k for all I going through those finite number of subsets. Then all the sets from C1 to Cn can be found inside of this largest collection B sub k. And since B sub k has the finite intersection property from being a part of the super subset B, this intersection, which is all of these C's, is not going to be empty. And that's what we wanted. We wanted to make sure there's always one element in there. Okay, so that's step one. There exists a maximal element, which that element is in itself a collection of subsets that have elements. But the idea is we can now say there exists this collection that's going to force us to choose something that will work, so that we can always be guaranteed compactness through the closed form of compactness. And this way, this construction is extendable to arbitrary products, whereas it wouldn't work in the box topology. So we do need one more little bit of hardware, otherwise it would make the actual proof really obnoxious. And this is just going to be two little small results that are helpful. If I have a set, and then I take this maximal collection, right? So we just proved it existed, so then once we do that, let's use it. Let D be a collection of subsets of X that is maximal. I keep getting the Transformers movie that just came out stuck in my head. Because it's like instead of Autobots, it's Maximals because they're animals that are robots. With the maximal. I respect to the finite intersection property. Then we have two very handy things. Honestly, they're very reminiscent of how topology is defined, which made me happy. So then it feels convincing. Infinite intersection of elements of this collection is an element of the collection itself. So the collections contain their finite intersections, which is very interesting. And then also, if we take a subset of X that ends up intersecting everything, so intersects every element of D, then that subset itself is going to be an element. A is in D. So we contain all the finite intersections of our collection, and boom, it's actually in there. And then if you take some subset that it has a shared common point with all the other subsets, then actually he's supposed to be in there. So he'll be in that collection. So let's prove both of these. It's slightly less complicated for whatever that means these days. Okay, so if I take B and I want this to be equal to the actually I don't need to be stated I just think equal the intersection of finitely many elements of script D. Now we're going to define a new collection. We'll call this script E. I'm going to take the previous collection that I just had, and now I'm tacking on this subset B. So the claim is basically, okay, here's a subset. We can't assume that it's a part of D yet, so I'll explain it. But then what's going to end up happening is that this is going to end up being the same thing as script D. Okay. So yeah, what I just said. So we want to show that E has a finite intersection property, because if so, then I like this word, maximality of D from the hypothesis implies that indeed those are just the same thing. So that we find that B ends up just being in B all along. So the way we do this, we'll take a finite number of elements, we'll take finitely many elements of our new collection, we're adjoining B. And now if we say we miss the one that we adjoin, so if none of them is the set B, then their intersection is non-empty. Now, why can't we just know that? Well, because we haven't actually included the adjoint set. So we're just still talking about the collection D itself. And the collection D itself has finite intersection property by definition. Or well, not by definition, but what we've shown it to be. So that's the boring case. The interesting case is when we're actually including B in our little selection. So if one of them is the set B, then their intersection is of the form I can take so from the script D, here's my D1, and I intersect a certain number of like n times, and then I'm adjoining this subset B. Now, we claimed in the hypothesis here that B equals a finite intersection of the elements of script D. So this set is also non-empty. So the logic here is okay. I've adjoined this guy, but I very specifically made this some sort of intersection of stuff that's in this family. Okay, well, great. Say he's actually in here. Well, all I'm doing is I'm taking stuff that I know is shared with D, with stuff that's shared with D. So it will still have things, even though this is technically adjoined, which forces me to be back in that collection. Okay. Okay, we'll make a similar argument for part B. So if this makes sense, then the part B will be very fun. So now I'm looking for the subset A that's going to intersect everything, and then that's going to put it inside. So given a subset A, define again an adjointment. So I'm going to say, all right, let's throw them up. And this is going to be my original collection. Together, we're tacking this new subset on. So we're going to show that, again, we just need to show that this collection has finite intersection property, from which we would be able to conclude that our subset is actually just part of this collection. So we'll take, again, strategy is pretty the same. Finitely, many elements of this adjoined collection. So if none, again, the boring case is if none of them is the set A, I have succeeded in choosing everything that already obeys the property I already wanted it to obey. So their intersection is automatically non-empty for the same exact reason as in part A. So that's why I just claim it automatic. And then otherwise, so the interesting case is we actually do have A in this batch of subsets. It is of the form. Okay, well, we took a finite number of things, so let's intersect a finite number of things. And now let's add on our subset A. Okay, well, believe it or not, we can think of this intersection to actually just be a member of the collection. Because what did we just take the time to prove for A? If I take a finite intersection of stuff, then any finite intersection then in itself is going to be back inside the D. So this right here is some sort of selected finite intersection, which means that whatever this element is, that's going to be also there. And then, okay, let me cite that so far. So then I'm going to put a parentheses here so you can see it. So if we think of D1 and up to Dn as an element that is contained in D intersecting A, this is not going to be empty by hypothesis. What does that know? The very hypothesis claim that the property that A has to satisfy is that it's always going to share something in the collection. Well, here's a finite group. We already proved before that, okay, well, if we take that finite intersection, congrats, you got something else in there. And that very thing, if we adjoin something, it has to intersect every single member. This ends up being a member, so then it can't be empty because we just assumed that that's the very property that it has. So it's true. So we can use these two facts in the proof to make the conclusion a little bit smoother. Okay. So now the actual theorem. Uh, Tychonoff. Yeah. Feels good to be here. It's been a while. Okay. An arbitrary product of compact spaces is compact in the product topology. Very profound. That's really cool that we can even say something like that. Because what arbitrary means is it doesn't matter how many. That could be an infinite number. And then within the concept of infinite number, it doesn't have to be even countable. You can have an uncountable number of compact spaces that you will actually have a product of, and that's still going to be compact. So what we're going to do is I'm going to define a set. This set is going to be a product. That's the Greek letter P for product over an arbitrary indexing set, and we usually indicate that by alpha and j of x alphas. So we have a whole bunch of stuff indexed over something that can be pretty much anything we want. Where each space x alpha is compact. So that's just what we state here, arbitrary product of compact spaces. So these are the compact spaces, and that's the arbitrary product. So we're going to let script A be a collection.
Scott?
Yeah.
Just to remember, does compactness mean that you can be covered by finitely many sets or something like that? Or
So there's two interpretations we can take of this. You can have the interpretation where I've got something, okay? And now, if I want within the space, if I have a collection of open sets, can I find a collection of open sets that if I were to take the union of everything, then I could get back that set or that space? Now, would be an open covering. This is only one example. There's an infinite number of ways I could actually choose to do this, but the key is for every single possible way I could cover this with open sets, I only require a finite number of them to actually do this, because you can get overlap, because if you're making your bed, you don't need every single blanket to technically cover the mattress. You've already done that with the bottom sheet. But then we add extra stuff, but you technically don't need those to still cover the thing. So we're saying, regardless of what kind of open covering you take, you will always be able to strip it down to just a finite number of things necessary to cover everything. So that's one interpretation of compactness. If you want to think about what we're invoking here for this proof is the closed form, which is if I take collections of the closed subsets, then if they satisfy the finite intersection property, I can take their intersections of all of them and still have something there. So it's not possible to intersect them all and then be missing a point. There is always going to be, so every single point can be found in one of those. So that's compact. It's not as intuitive as like connected. So don't think of compact as connected. If you start thinking about that way, then it breaks down once you start exiting just the familiar, two-dimensional kind of examples. Because there's no way I can draw for you an arbitrarily infinite product of spaces. And then say, well, yes, I can imagine, what that would look like with keeping everything covered up, right? So that's why we're using the closed form. Because if I can guarantee the existence that I can choose an element that's inside of that intersection, well, I've forced it to not be empty, which means it's going to have to be compact. Was that somewhat
sort of
okay? There's a lot going on all the time. The collection of subsets of X having, you guessed it, a finite intersection property. So if we prove that this intersection, so if I take the subsets of my collection and then their closures, you might be wondering why the closures, and I'll actually probably have time to talk about the motivation for this, because there's kind of a nice visual when you can motivate that. So as long as that's not empty, then it follows that X is compact. That's kind of the whole point of the chart here, showing that this is compact. So we can apply the first lemma, because I know that you have perfect memories and remember exactly what the first lemma was. We can choose a collection script D of subsets of X such that script A is contained inside of D and script D is maximal with respect to just it. That's finite intersection property. Yeah. So the very first thing that we did was we talked about the very existence of this. So that's what I mean by we got to cite the lemma for that. So it suffices to show that this intersection, where we're looking at our elements in the maximal collection and their intersection of those closures, is non-empty. Why is it sufficient? Well, because this is if this is maximal, then it's either going to be the same thing or bigger. It's going to contain more. So this is actually stronger than this. So given some alpha and j, doesn't matter what it is, doesn't matter what the indexing set is, and it doesn't matter which index. We're going to define a projection map. So P for projection, so alpha, to indicate that we're doing it for the alpha index, is going to actually map the whole product onto just its dimension.
So is this like function?
Think about it like this. So suppose you have, this is a familiar thing. If I take this guy right here, and that's say x1 and x2, and this right here is the space x1, and this is the space x2. What I'm really saying is I'm taking this p map, and that's shooting it right down onto here. So I'm projecting it, and this would be the projection for indexing it with 1, because the index is 1 here, of the element x1, which is in x1. And this in here is an element of x1. Whereas if I projected it this way, now this element right here would be the projection indexed for 2 of x2, and that as an element of x2. So that's what we're saying with this. Now just do that generally. Doesn't even matter how many we have in any direction and whatever. And now I think about it, we're not requiring this to be metrizable. So who knows? Direction is meaningless, actually. It's just stuff. So this be the projection now. As usual. I love that phrase. That basically says we don't have to define something obnoxious in the middle. Let's get on with it. Consider the collection. And I'm going to now take all of the image of the projection of alpha from some element D for all of the elements that are in this maximal collection. So now think about like conglomerate blobs of stuff. And say this is some x1, say this is some x2. And now these blobs, these are the D's. So this is like D1, D2, D3, D4, and I'm projecting onto here. So it's kind of flattening out onto, so this would be like that image projection. So then I take that and I'm collecting all of these. So I'm smashing it down here. I could have smashed it over to x2, and arbitrarily I could just smash it onto something that doesn't, I can't really visually represent it. Just extend the point idea into an image. And then these are subsets of their respective axis or space, or however you want to think about that, x alpha. So this collection has finite intersection property because, well, D does. Moving on. So by compactness, of x alpha, because that's part of what the theorem allows us to assume is that they're all compact. We can, for all the alphas, choose a point x alpha that's in x alpha, such that my x alpha can be found inside of the intersection if I take all of those D's in the collection, and then the projection that I get when I project the image of each D and then close it. So we can choose something in it. So basically, what this means is in a simple case, if we're looking again at this, if we only had x1 and x2, suppose my collection D is this collection of subsets. Right, so this is D1, D2, D3. Now I'm saying, okay, step 1, project it onto the appropriate axis. So for P1, I'm projecting all of these, the image of it down onto. But then on top of that, I don't want to leave any holes. So I'm actually going to close it. So then now this is closed. And then I'm just making sure my choice of X alpha falls somewhere in here. So that when I shoot it back up, it'll be found in the intersection. And then we can do that for all of them. So because you could project it this way and it would come across. So that's why we close it, is we don't want it to be open down at the when we project it. Because it could be the endpoint that requires the choice. We can do that. Okay. So we're going to let x indicated as a vector to be now the tuple x alpha, where alpha is in J. So this is like, take the chain. If I had, typically we think of this as like x1, x2. Well, this is the case, very simply, of x alpha, where alpha is in the set 1, 2. So this is important. Now, that could be uncountably long. So you get sequence. This is a point of x. So we want to show that if I have x, we basically want x to be in a closure of D for every single D in our collection. Because then we've done exactly what we came to do. Our proof is complete. Okay, so home stretch. Kind of technical, but it's far less disgusting than the verticell lemma was last feature. Okay. Well, we first we show that, and this is kind of where it gets a little tricky, but so suppose we have an index beta, okay, so we have one of these, and then we're going to take the inverse image of a neighborhood around a point that's containing that choice, x, and that particular space. So if this is any sub-basis element.
So wait, does inverse mean that you're going back to the general one?
Yeah. So remember all the blobs in the middle,
Yeah.
and then we smashed it down to project it.
Yeah.
But now we're saying, oh wait, never mind, go back. So we're throwing it back up, and that's what we're talking about. Which specifically, then we're choosing a neighborhood around the point that we selected.
Okay.
And then that's what we're spitting back up, and we're saying, okay, let's make this a sub-basis element. Specifically for the necessary topology, obviously. So for the product topology on X containing our chosen point X, then this P sub beta inverse image of the neighborhood around X beta in beta intersects every element of our collection. Right? So that's kind of the goal. So the set U sub beta, this is a neighborhood. And think about that as intuitively as you can. It's literally just like things around, nearby, containing a neighborhood of X beta in X beta. So since X beta, the point, is contained inside the closure of projecting onto the beta axis of the image of that chosen element E, then by definition, then that means our neighborhood intersects, when we project and smash it all down, the projected image of that element D in some point T B of Y, where Y comes from B. So then So basically, if you have a neighborhood, it's not just one guy.
Yeah.
You've got some points around, so then you can find something else that's not X that came from the same thing that you can project out, and that's contained inside of your neighborhood. Or more at the logic is the existence of such a neighborhood allows you to say that you can find something that would project out to it. So then it follows that Y can be found. This is a restatement what I just said, and that inverse image if I shoot it back up from the neighborhood, intersecting with D. So it follows from B of the previous lemma that every subbasis element containing X belongs to the collection. So, because remember, part B said if I take something that can intersect with everything in the collection, then it's got to be in it. Well, that's exactly what we just found. So we're going to claim that, and then we can use part A. It follows from part A, which was about taking a finite intersection of stuff.
Mhm.
That every basis element containing X belongs to D. And since D has a finite intersection or property, then this means that every basis element containing our chosen point X intersects every element. Intersects every element of D. Hence, if I have X in the closure at D, for all the D in D, as desired. Cool.
Well done.
Do you want to? I went through the stone check compactification, but it's already we got like 10 minutes. You want to call it a day?
Yeah, I think so.
Alright,
That's good.
it's enough
Yes.
mathematics for a day.
I like it.
How did your class prove it? Because there are like 3 different ways you can get to it.
Yeah, we used the compactness, but we didn't do
Didn't do it from Zorn's lemma.
no.
My guess is if you were doing it through the calc track,
Right.
then you would have proved there's an intermediate theorem that implies this basically as a corollary. So, you know,
I mean, it wasn't a big focus of the class. It was probably needed to do something later.
Yeah.
As a tool. Where in topology, it's an important focus. Cool. Well, cool. All right. Well done. So you got plans